Okay, great. Awesome. Thanks for coming, everyone. I'm really excited about today. Can I see a show of hands of who was not here for the last talk? Oh, okay, great. And then can you show me, can anyone show me who's not comfortable with Q learning, like does not sure that they really get Q learning yet? Not. Okay. So I did cover Q learning last time, but I was a bit rushed at the important bits, so I'll try to review that, not like kind of quickly, and then so I can get through the DQN stuff. So I'm going to skip all the intro that we went through, except just point out a couple things. So there's a new fastest computer in the world. That's with the Department of Energy, and so they're the new bar on that. I added that to the top left. And so that's saying that they could do AlphaGo 0 in a day. I am probably always going to show this slide. When Elon Musk says he's afraid of AI, he's probably not afraid of autoencoders, right? He's probably talking about RL. So the ethics part is actually really important, I think, in this stuff. The RL is bringing things closest to the real world. It's not there yet, but it's going to be. Okay, so I have another one for that. Okay, so we're just jumping through what we did last time. You can see it on YouTube. Bruce made an incredible YouTube video of the talk last time, so I hope you guys can catch it. So starting with Q learning. The Q function is representing the state action value. And Q learning belongs in this area here. This is the different types of RL because the Q function is a value function. The value function is trying to estimate something about how good a state is or how good an action in a certain state is. Now, that's not the only way to do things. There's all sorts of other methods. Policy-based methods, actor-critic methods combine value functions and policies, and then model-based functions add a model of the environment. Yes? Yeah, sure. So actor is the part of it that chooses an action, that decides what action to take. And if I just go, actually, if we look at it here and maybe make it a little more clear. So when I say that we have an agent here, so this is the canonical clock cycle of reinforcement learning. The agent is getting a state or sometimes an observation more generally, but here we'll say state. It takes an action and then it gets a reward, and it keeps going around like that. Now the agent is really just some kind of machine or function that chooses the next action. That's the most general way to talk about what an agent is. And we say pi is a policy. Policy means how to choose what to do next. Now, what's inside the policy depends on what type of RL you're doing. It can be simple, complex, it can have value functions or not, but no matter what it is, it's a policy, and it's a pi. So when we talk about a value function, we talk about a Q function, it's actually wrapped in a pi function. But most of the complexity, in Q learning, most of the complexity is inside the Q function, and the pi function is actually just like a thin, simple shell layer on top. And we'll get into the details of that. So here I'm just pointing out that value-based could include state action value function, that's Q, or a value function, or an advantage function, or one or more of those. And then Bruce asked a great question last time. He said, when we have a Q function, is that estimating the state action value for like the optimal actions going forward, or the average, or what type of? So really, I had oversimplified the notation last time, and so I just marked that up a little to make it a little clearer. And so a Q function is with respect to a specific policy. Same with the value function. So the value of a state really depends on what the policy you have to work with. If you're using the optimal policy, then your value function of using that policy can be the optimal value of that state. But if you have a really bad policy, then your value might be either inaccurate or it might not reflect what the value under an ideal policy would be. Is that clear to everyone? Yeah, okay. So the subscript pi sometimes is dropped, but it's kind of important because it's with respect. So here we're talking about Q with respect to a certain policy. Okay, so high level Q learning is learning this function which estimates the expected sum of returns, sometimes discounted, but expected sum of returns from that point. So I use the example of a really simple example. You're playing tic-tac-toe. You're in a certain position in the board. What is the expected payoff of the different options you have? That's the Q function. And the Q function implies a policy. Once you have the Q function, your policy is super simple. This is what I mean about the thin shell. There's almost no logic in your policy in Q learning. That's not the case in some other types of RL agents. But in Q learning, the policy is really super simple. So we use what's called temporal difference learning to learn that Q function. I find the terminology, when I first got into it, the terminology is a little confusing. Why do you need TD learning and you need Q learning? But it's actually, yes. So the output is continuous for each action, but there's a discrete number of actions. And that's different than some other forms of agents where you can have continuous actions. It's not, Q learning, vanilla Q learning can't handle continuous action spaces, but each Q value itself is a continuous value. And we'll see an example about it. So, and that's what I'm trying to say here. But Q learning can handle some different cases like, yes? Yes. Yes, that's the goal. Yes, to learn. Can you repeat the question? So, right. So the question was, are we going to learn the optimal Q? Is that the goal? Yes, that's the goal. And we'll talk about these other, changing environments. So this is saying Q learning can handle the case where your environment drifts, like the rules of the world maybe changing over time. If it's slow enough, Q learning can kind of adapt to that. Some systems wouldn't be able to do that. Yes?
But, so just to make it concrete, tell me if I'm wrong. If you had a Q function for tic-tac-toe, you can kind of see the Q function as like a probability of winning given the state and the action that happens that you choose for that state that you're in.
Quite similar to that. We'll see an example in a minute. It's not exactly that. So the point of this slide is to say Q learning is not like, it's kind of naive in some ways. When you understand what it's doing, you realize that it can seem to act smart, but there's a lot of things it's completely ignorant about. For example, when maybe I'll get to that. Okay, here. So here we're playing tic-tac-toe. This is a system I made to explore Q learning called AlphaZos. And each action is represented by a square on the board. The actions you take is putting a piece on the board. The Q values are shown at the top as the bars. Green bar is positive, red bar is a negative value. So the way that I decided to train this system, to answer your question, is that when you lose the game, you get -1 point. And so the Q values are actually going from -2 to +1. So it doesn't precisely correspond to probabilities, but it's similar to that. And there's also a decay function that's applied. The intuition with Q learning is when you're in a state, you have all these doors, which are your different actions that you can go through. Going through a door is taking the action. So you can think over here, each of these is like a door, and picking one is picking that action and walking through that door into the next state. Now, what you do in Q learning is, when you're done with Q learning, every door has a little label on top, which has this little bar that tells you what the Q value is. So the best thing to do when everything's trained is you look at all the doors and you pick the one with the best value and you walk through that, right? But Q-learning doesn't have any idea of where you end up going after you walk through the door. It has no sense of what the next state is, and that's kind of important sometimes, right? So that's one reason I say it's quite naive. It has no sense, like when it decided to pick here, because this was the biggest Q value, so it placed the piece there. Okay, this is the DQN agent is the robot face. It picked here. It picked this one because it had the largest Q value. But there's nothing in the system that knows that when it picks this action, that results in a piece going in that spot. It actually doesn't connect those two things. It sounds ridiculous, but that's how it works. It doesn't even know it has no concept of what that action means. And I don't mean in the sense that computers don't know what they're doing. Of course they don't know what they're doing. I just mean there's nothing modeling in the system how one state leads to the next. It's figured out through learning that that's the best action to take, which is, and I just numbered them, right? 0, 1, 2, 3, like that. So it's determined that action number 7 is a good one to take, but it doesn't know why. It doesn't know what happens when it does that. But the environment then takes that action and puts the piece on the board. Okay, the agent doesn't have a clue. So vanilla Q-learning is quite naive and quite naive that way. That was the point of the dog slide. Okay, so this is just showing another example where there's Q values. I just wanted to point out here the Q values. This is DeepMind system. The Q value, and this is DQN in this case. The Q values are very similar to each other. There's only just small variation, and they'd all be going up and down according to how the game is progressing. But sometimes it's the smallness of the variation between the Qs makes for some interesting effects sometimes. So this is just another example. This is my system again, AlphaZos, playing Connect 4. And so you're seeing again, in this case, the actions are the columns. You drop a piece down, you're picking the column. So once again, it picked the one with the largest Q. So temporal difference learning is at the heart of Q learning. And the point of it is, it's actually a very simple thing. The purpose of it is to predict future values from values experience. And it's made for a situation where you keep experiencing trajectories or rollouts or have experiences in environments. So the next time you come through, that's the temporal difference, is you experience something the first time through, and you estimate some Q values as you go, and then you reset the environment and you walk through the same environment again, but now the values are slightly different. That's the temporal difference. Like the next time, it's a bit different. So this is temporal difference learning is old. It's not new, right? DQN adds some new thing. Yes. So yeah, in the subsequent rollouts, are you experiencing the same path through? Ideally, no, because you want to explore the state space so that you can learn about the value of all the different possible actions. And then once the agent has that experience, it's rolled that experience up into the learned Q value, and then it can perform well. Does that make sense? Yes? Yeah. I think it'll become clear in a moment. That the future slide will show. Okay, it can actually be used for different things, but in this case, future values of Q. Yeah. So TD learning is kind of a very simple thing. The example I made this chart to show, a simple example, is in this environment, imagine you walk down a hall, and this is 9 steps down the hall. You get no reward until the last step, and when you get to the end, you get a 1 unit reward. This is 1 reward, right? Now that's a real reward. That's not an expected reward or a Q value. That's a real reward. So 0 all the way and then 1. But what TD learning does is every time through the experience, remember I said as it's walking through the door, as you walk through the door, you get a reward from the environment, and you get to also look at the Q values in the next room. Okay? So you can look at the Q values in the next room, and you look at the rewards you got, you add them together, and you write that on the door that you just walked through, and then you walk through. So if you think about that, every time you walk down the hallway, you're going to mark it on the previous door one step back. Because the first time you'll mark it on the top of the second last door, because you're seeing you're getting the reward, and so you're marking it. And then the next time, when you're walking in the previous door, you're seeing that reward that you marked on there. You're not getting a reward, you get 0, because you get no reward until the end. But you're seeing the Q values that you had marked. You got 1 reward on a door in this room, and so you add that to the 0, and you mark it on this door. And then the next time you walk through, you see it on the previous door. And so you're carrying that knowledge of the future reward back through the doorways, back to the beginning. So in vanilla TD learning, it actually takes you 9 times through this hallway to mark all the doors all the way back to the beginning. And once you've done that, then you know just from looking at the first doors what your expected reward is. That's TD learning. It's that action of marking on the door. Yes. So this is a very simplified example, but if you're getting stochastic rewards and things, I'll show how it iterates and converges. It's a good question. Yes, you can have some stochasticity in all of these things, and Q-learning will kind of help you find the expected value even under that uncertainty. Yes?
How is this information stored?
Well, that depends on what type of Q-learning you do. In DQN, it'll be stored inside a neural network. In tabular methods, it'll be in a table. Was there a question back there? You can store it in different ways, and I'll talk about the different ways that it could be stored. And if you, TD learning itself is, I think it's a little more abstract. It doesn't tell you how you're storing anything. I don't think of it as like a complete algorithm as so much as like just a little building block that you use in different ways. And so TD learning would be used to provide the value, the Q value, to train your network against. So David Silver famously says, reinforcement learning plus deep learning equals artificial general intelligence, and reinforcement learning provides the objective. So that's the TD learning providing the Q, and then deep learning is learning that objective. So that's how they fit together. If you still have that question later, let me know. Yeah, yeah, you could. I mean, the simplest way is to store a table, store a list of in every state, every action, and what's the value, and then iterating on those values. Does that make sense? Yes, you could extend that as much as you want. Yeah. Well, I think actor critic can use TD learning as well. It'll come up in different places in RL. It's not married to Q learning. Yeah. Okay, so this is just to say the vanilla Q learning uses what's called one-step TD, or also called TD0. That's only updating the previous doorway, the one step before. You don't have to do it that way. There's n-step methods and lambda methods as well, and they can. It's basically using the same idea but updating multiple doorways at a time. Now, and Monte Carlo here. This is Rich Sutton trying to say there's a whole spectrum of different approaches to this, and we're up here right now with temporal difference learning. But there's also Monte Carlo where you just go through the whole. If you want to know the value, you actually walk through a whole experience and just remember that value. I'm going to ignore the dynamic programming side because it's only relevant if you know the entire MDP. So this graph is just to show that, when we said that you could update multiple steps, someone asked me last time, if you're playing a board game or something, wouldn't you want to update the values all the way back in time to the beginning? It sounds conceptually good, but it doesn't always result in better outcomes, because you can see here, N1 is the single step TD, and this is the alpha. This is the learning rate. So just imagine you pick the best learning rate. Right? The best learning rate, the best you can do, the best you can do with the error is that low, right? You want to get the lowest error you can. But with a two-step method, you can get lower. With a four-step method, you can get even lower. But as you go higher up, as you have increase n even further, it doesn't get better. So this is just showing that it's not always better to do larger number of steps in your TD learning. So Q learning is based on Bellman's principle of optimality from dynamic programming, and it's this kind of a simple thing which just says, if you have an optimal path, then the parts of it are optimal as well. So when Q-learning, when it's fully trained, this quality will hold. This is Bellman's equation. This is only really true if your Q function is already trained. And what it's saying is that the Q function, or the Q value, like I said, what's written on top of the door, equals the rewards you get at that point, going through the door, as well as the largest Q value on any of the doors in the next room. It's quite simple. There's also a discount factor applied here that makes it prefer getting rewards now instead of later. And that can be 1, in which case there's no discounting. That discount is the reason, by the way, that this was curving down, because I put a discount on there. So what that means is if there was a way to win the game in 1 step, it would prefer that than finding another strategy to win it after 7 steps. So this is only true if your Q function's already been trained, it's converged. How do you get it there? So this is how you get it there. You can start, in many examples, you might start with a Q function just to always return 0. It's one way to do it. Or if you're using a neural net, your Q function might just return noise from the neural net because it's not trained. Or whatever method you use, in the beginning your Q values are wrong. So what you do is, you run through your experiences, you make some rollout trajectories, and each time through, you update the Q value just a little bit. A little bit meaning this is the learning rate, so that might be like 1% or 10%. So you're changing it by 10%. Now it's usually written this way because that's how it's implemented in code. But I like thinking about it this way because it seems clearer to me what it's doing. So what it's doing is it's taking the existing value to the proportion 1 minus alpha. So if alpha was 10%, then it's 90% keeping the existing and 10% using the new value that we're seeing. But if this is from the future, it's kind of weird. Imagine the first time you're walking through the doorways. All the Q values are wrong. You walk through. you are updating your Q value based on this future Q, which is wrong. But you're also incorporating the rewards you get right now, which you know is correct because you're seeing it right now. So you're combining this future estimate with something you know now, which is the rewards you get, and that's the part that makes it a little more accurate. And then as you keep doing that, if you keep iterating on this, you're converging to the true Q. It's kind of a strange process, but it works.
So does alpha define explore exploit?
Does alpha define explore exploit? No. Alpha is a different thing. The alpha is talking about how quickly it's going to update the Q values. It's kind of like the learning rate in a deep learning. It's like how fast you're updating. So if you had this at 1.0, then it would just completely overwrite the Q value with the new one each time. If you had it really small, then it would converge very slowly. Is this slide okay? Because this is key to the whole, this is the guts of Q learning right here, this slide. I've never seen it, guys, I've never seen this written out so clearly. These two slides here. I took a lot of pain to really, because everyone who covers this, they cover some little angle of it and they copy and paste from somewhere, but I've never seen it really explain this clearly. And I don't mean that in an egotistical way. I mean, like, it bugged me that no one explained it that clearly. Yes? Yeah, excellent question. So there is some theoretical guarantees, but the conditions, let's see, guarantees. The conditions, and don't quote me on this, but this is what I'm getting from everything I've read. You have to visit infinitely and try infinitely, and your learning rate schedule can't be too high or too low. It's got to be some kind of medium value. And these sound kind of constraining, but in practice you don't need to visit everything infinitely. It's just to make the theory work. I would describe it that way. I don't know a better way to answer you. So in vanilla Q learning, you're not multiplying the transition matrix. That would be more like maybe a dynamic programming approach. Yeah, I'm not sure how better to answer your question right now. No, it's just an example. And actually, you would want to change that. You may change that over time, or there's a lot of hyperparameters here. And I'm not claiming to be an expert in how to set them all. Okay, so these two slides are key. If you see the slide deck afterwards, you can come back to this and try to see what's going on, okay? The algorithm's written out here, the vanilla Q, if you want to see it for later. Okay, policies. So this is getting to the exploration question. Policy is the course of action. Okay, so you have these Qs, now what? What do you do? In vanilla Q learning, there's many ways to do it, but in the most vanilla textbook way of doing Q learning, you have two types of policies. One that you use when you're fully trained. Obviously, when you're fully trained, what are you going to do? You're going to pick the best Q at every point. Sensible. It's going to lead you to the best victory in your game or best outcome in your medical situation or whatever it is. That's the point of the Q function. But when you're training, usually Q learning is called off policy. That means when you're training, you use a different strategy. And you're using an exploratory strategy. So you get to learn about the space. And in that learning, you're gathering the knowledge that will let your Q function actually be optimal in the end. If you don't explore, then you're never sure that you're not missing something important. So epsilon greedy is a simple policy where you pick a random value every time, with a random probability. You either do the usual thing, which is called greedy. Greedy meaning pick the best. Or if you roll the dice a certain way, you pick a random action. So if you do that enough times, you will end up exploring the different avenues in your, just imagine your state space, exploring all the different lefts and rights and turns and all that. And you will start to get a sense of the cues because the TD learning will pull those cue values in from all the different avenues, right? Yes, Anchan. Well, yes. In vanilla Q learning, it's just in training. I might point out later there's some cases where you might want to do some exploring even when you're done training, but that's not here, this vanilla. That's an excellent question. Not in vanilla Q learning. There's all kinds of extensions to it. You might think, if you know about a state that's very similar, maybe the Q value is very similar. So that is really the whole point of DQN. DQN, when you have like what a neural network does is it smoothens out the difference between the different states. And so it tries to help you say, hey, I haven't seen that exact state, but it's kind of like, right? So it estimates based on similarity. Yes?
Do you see like people take epsilon and decay it over time?
Yes, you're supposed to do that. Yeah. Yes, and I can talk more about why. Okay, so we call the training policy the behavior policy. That's what it's doing. That's how it's thrashing around. And then we call the policy, when we're done, what we really want is the target policy. That's the train policy that picks this is the optimal policy that picks the best. That's called the target policy. Now, why don't we just, for training, why don't we just always roll the dice? Why don't we pick randomly all the time? Anyone have any idea about that? Because then we'd get through all the different avenues, right? Why wouldn't we do that? Why do we do this funny thing where we exploit 80% of it? By the way, is everyone comfortable with explore, exploit? Okay. So why wouldn't we just go random all the time? Anyone? Maybe yes. I think that's getting there. Okay, yes. I think there's something to that for sure. Yeah. Yes.
More valuable to explore states that you already know are relatively good, like try to optimize from like a relatively well. Like it's better to go in a direction that you kind of know is the right way than go the opposite.
Yeah. You know what? You guys are all yes. Definitely, the exploration is trying to avoid that locking into limited state space. But the thing about, and some of you guys touched on it in different angles. But if you think about, imagine a chess game or a game of Go. If you're exploring randomly, it's going to be really hard for you to get good at the end game. I don't know if Go is the best example. Let's say even I experienced this with training tic-tac-toe. If your agent is choosing very randomly, then it doesn't often end up in an end game situation. But with epsilon greedy, sometimes it's choosing the best, right? And then it can end up in an end game situation, and then it chooses randomly in the end game. So it's kind of like all of you guys were saying something along those lines. But the intuition is, I think like what you were saying, Matthew. Actually, there are many answers like that. So if you can do it fully greedy, you can do it. It will bring you some results, but it might be so inefficient that you'll never get good at the end game. Now I'm saying end game. It's not all about games, and sometimes it's continuous learning or endless episodes. There's different scenarios, but it's a useful thing to be able to balance that exploiting and so you're kind of going further and branching out and going further and branching out, right? Does that make sense? Okay. And then target policy. Is 100% greedy always the best for the target policy? Well, I said, that's what you're supposed to do. But if you look back here, this is what happens when I run this game. Or you can maybe see it here too. Look at how similar these Q values are, right? They're so similar. Here, why did it go there? Why wouldn't it go there? It's symmetrical board. Why did it pick down here? Actually, it's deterministic. Unless you add something to add stochasticity, this is totally deterministic. So let's say through the numerical optimization, just through the random chance, this one ends up 0.001, the Q values, that little bit, epsilon, a tiny delta larger. The Q learning thinks all these are not worth going to. This is somehow the best. Is it really? Not really, right? So that greediness is kind of over-constraining in some way, sometimes, right? So depending on your scenario, I might want to run this with a little bit of noise, even when you're playing against it, right? There's different, it depends on what you're trying to do. But it's easy, if you just do vanilla Q learning, that's the thing with all of RL actually. All the components are kind of, and if you watch David Silver talk about it, he says this all the time. Don't take it as gospel, how these things are composed. You understand the components, and then you combine them as you need it for your particular problem. Okay, so epsilon greedy is like the simple way of exploring. It's actually what DeepMind used in the real DQN, so it can be used. It's not always the ideal way, and you can look into a whole bunch of other methods, and I'm not going to go through them. But there's a whole bunch of other ways, depending on what you're trying to accomplish. Okay, on policy, off policy. So we said Q-learning is doing epsilon greedy when it's training, that's the behavior policy, and totally greedy for its target policy. And they're not the same. That means Q-learning is off policy. If the two policies are different, it's off policy. If they're the same, it's on policy. Now, there's a on policy variant of Q-learning that's almost the exact same algorithm, but it is on policy. That means it doesn't use a different strategy for training and for when it's deployed, and that's called SARSA. And I'm not going to go into it, but just to quickly show you the intuition. This is an example from Sutton and Bartow. And the idea here is here's a world where the agent's starting here, and its goal is to get here, and it's just walking around randomly. It has no idea what the goal is in this world. It's epsilon greedy is going to make it walk all around, right? And this is the cliff. If it walks down here, it dies. It gets some negative reward. So if you run Q learning, there's some negative move for each step. So it's trying to minimize the number of steps. And there's a big negative reward for falling off the cliff. Now Q learning is going to, through exploration, find that the best way to get there is just walk along the cliff and go down here, which is the optimal. However, SARSA is going to notice that when its randomness makes it walk off the cliff, it's going to notice that that's hurting its score. And so from its perspective, the optimal is actually stay far away from the cliff and go down here. So, and it's almost the same, but it's just, well, all it does is instead of saying max, in that place where it says max, picking the max, instead of doing the max, it just does, it just records the Q and the action that it did, not the max action. Yes? It randomly picks up, down, left, right each step. The action is the direction for the next step. Yeah. No, in this one it's deterministic. There's some that have wind and some weird things. This one doesn't. I don't think this one has any of that. Well, maybe it depends. If you want to actually deploy a robot in the world, would you want it to walk along the cliff? Like maybe some wind would actually blow it off. Yes, you're absolutely right. If it's totally deterministic, this is optimal. So SARSA ends up with a policy that builds in a bit of that safety, which sometimes might be useful. So it's just something to know about. Oh, in the reward, yeah, because it's not falling off the cliff. It never falls off the cliff as it's training. As it's training, it learns not to go near the cliff when it's training, right? So it's epsilon greedy keeps it, even the stillest, it keeps it safe. Well, I think this is while it's still training. So it's still falling off sometimes.
So, like, looking at this, SARSA will be 4 points less effective than Q learning at the very end, right? So, but there's such a huge, like, negative consequence of falling off the cliff that if you look at that graph there, I think it will eventually converge and Q learning will be slightly higher. But because Q learning is falling off the cliff, like more often, because it's sort of trying to take that optimal route.
Oh, yeah, to your point, there's stochasticity here. See, it's saying epsilon greedy is 0.1. So this graph is with respect to the epsilon greedy policy. It's when there is still that little bit of randomness, right? And then this path is showing the target policy, the final train policy. But this graph is showing how it's performing when it has that little bit of stochasticity. So you know what? You were right and I was wrong when we were describing that at first. So in this world is deterministic, in this is not. I mean, in the top paths. Does that make sense?
SARSA is
okay.
Because it still is epsilon greedy.
SARSA can be using the epsilon greedy, but policy, but it doesn't have to. Okay, so this is, I don't know, is this going to work? Yeah, okay, so this is showing Q-learning training. So what you see is it's pulling the green values back towards the front, right? In the beginning, it's all black. Let's do that again. Notice in the beginning, it's all black, and then as it gets to the end, it updates the doorway, which is that action, and it pulls that back. It also pulls the red back, and it's pulling it towards the starting point, starting down here, right? I put this one as a backup in case the video didn't work, but this one's better. So as it's training, it's building that surface that it can just follow. So when it's fully trained, it knows exactly what to do and it can keep doing it. Notice that the green, if the red and the green, if a negative reward and a positive reward ever intersect, the positive reward or the better reward will take precedence because it has that max selector. So if you enter a room and there's a horrible door, that doesn't matter as long as there's a good door.
What happens if you train this model and you find the door successfully, and then you block one of the positions in the room, so it's not out of the water and get to the door? Does someone remember if this will be in your room after you find the door?
Oh, good question. Yeah, if you trained it further, it should be able to adjust. Not right away, but over time. It would continue to iterate and converge on the new cues. Yes. This is not, so vanilla cue learning doesn't involve replanning. Replanning would mean, oh, that's not working out, let's find another path. It doesn't do it that way. You can incorporate planning, but then you end up with Dynacue, this whole different thing. I'll show you how that all. I'm not going to go into Dynacue, but there's other ways. But that's not. And you might say that's disappointing, the Q learning, but think of Q learning as a component, right? Oh, sorry, this is not very clear. So if you're here, then this is up. There's the four actions you can take. So yeah, it's like joystick view. So this is the value of the action going up in this state. And this is the value of going down in this state. Does that make sense? Pardon? Yeah, it starts from down here, yeah. Yeah. It starts from here every time. It doesn't know that this is a positive reward and this is a negative reward. It explores and finds that. And then over time, it's pulling the Q. So, yeah, so these numbers are the actual Q values. And you see, for one state, there's 1, 2, 3, 4 Q values because there's 4 actions. Because Q is a function of S and A, the state and the value, state and the action. Does that make sense? This example really helps understand what's going on. If you understand this and the Bellman stuff, that's the guts of Q learning right there. Okay, so tabular methods. How many states do we have to deal with? Can be quite a lot. You know, if you just keep a table, like here, this is a tabular method because you're actually writing down the number and storing and updating every. So if you were to count all of these, you would be storing in a matrix somewhere. How would that matrix look if you're playing Tetris, 10 to the 60 states? How would the matrix look if you're playing Atari? It would be quite a large matrix. What if it was continuous? So now if we try to discretize these robot controllers, so the robot controllers, the way they work is, if they want to move an arm, they're actually, the control is to send a torque, like you're sending current to the arm, to the motor, to make a torque happen on the elbow or something. And that's like a continuous value. Here, our actions are all discrete. You're choosing action 1, 2, 3, or 4. There's a fixed set of actions you can take, right? And here, you're choosing column 1, 2, 3, 4, whatever. You're only picking one of those actions. The Q values are continuous, but the actions are discrete. But here, the action, you still have the action that you pick is actually a torque for your joint. So that can be any real number. So that's like some huge space. And so what they're saying is, if you discretize it, if you cut it, if you try to make this continuous thing into like, okay, I'll call that position 1 and 2, it explodes. And so your tabular methods are not going to help you. Okay, this is motivating the next section. Okay, so Q learning methods. I'm not trying to be comprehensive in this list, but here's some different ways that Q learning can be used. Tabular is what we showed in the example. FQI I was reading through medical literature for chemotherapy and things that kind of like older papers in medical journals. Using Q learning, they would use FQI. And that is a batch mode thing where they'd get a whole bunch of data and they would fit their model all at once. It's different than DQN is learning online, like as it's playing, it's learning. It's a little different. So yeah, with FQI, you can use different types of function approximators. It actually doesn't matter what you use. With DQN, the guy who was the mastermind behind DQN was saying his goal was to try to make Q learning look like a supervised problem. And we'll see how that plays out. And so in that case, you're training a deep net. There's also, you can imagine Bayesian versions of this, and you can look that stuff up. Okay, so finally we're at DQN. Is there more questions on Q learning before we proceed?
One more question. This relearning concept. And so with your robots, you train your robots, do a movement, and you found a solution to it, and then eventually they build up wares and bearings, things like that. Does it need to be retrained to be able to find its goal? And is there a concept of continuous learning?
Yeah, you could do continuous learning. Yeah. If your robot wears out, so the actions don't do what it thinks it's doing. Yeah, that's actually a common problem in robotics. And in the model-based, they would often use model-based methods for robotics that lets the agent have a concept of when it moves its arm, what's actually happening in the real world, which Q-learning doesn't have any concept of that. And that model, if there's a little mismatch between the model and reality, then that causes cascading errors that end up with the robot not being able to perform. So yeah, that is definitely an issue. It's not in this we're dealing with a hermetic, simple world at this point. It's not an issue here, but yeah, absolutely, that's a key concern in robotics. Yes, that's what the n-step Q-learning, n-step TD is. Like this is two-step TD. You would look through the next door and the next door and look at those, right? So yeah, you can do that. That's what this graph was trying to show. Is how good of an idea is it to look through, in the future? It makes the algorithm more complicated. Like one thing in DQN is the data structure is so simple. It's super simple because you're only looking one step ahead. So you just keep a list of, I was in this state, I moved to that state, I got that reward. But if you start having multiple steps, then your data structures get more, there's more stuff to keep track of, right? Okay, any more questions here before we get into DQN? Because there's a lot in here. Is it really 7:15? Okay, I'll try to speed it up. All right, so there's the algorithms in reinforcement learning can be arranged in this way. We are right here in Q-learning. So remember we said there's value methods, policy methods, but DQN is dealing with discrete actions. It's model free. It doesn't have a model of environment. It doesn't know what the environment is doing. It's off policy. That means it's epsilon greedy is not greedy, and it's not based on derivatives. So the policy gradients, there's all this other math in here that we don't have to get into. DQN is relatively simple in that way. So David Silver said, I mentioned before, when you combine deep learning and reinforcement learning gives you the objective, what you're trying to learn, and deep learning gives you the mechanism to learn that with those smooth neural networks, yes? Yes, but I don't think I have a very simple way to explain to you how they're related. But if you want to know in more depth, the Sutton and Bartow book or the David Silver lectures go in depth. Yeah. Yeah, the Bellman equation is a thing from dynamic programming. Okay, so how did we get to the point of DQN? Well, there's this thing called the arcade learning environment, which is programmatic interface to the Atari games that different people were using to test their AI agents against. And that all happened before we even got to the DQN papers. So here you see, this is the paper where they presented the arcade learning environment. And then the DQN papers came along and they were targeting that environment. So this is actually the second DQN paper. There was two key papers. This is the neural network that was used in the second paper. And basically two convolutional layers because it's dealing with the image. What it's looking at is it's looking at the Atari screen, either the raw pixels or the memory, which is representing the pixels. And it's outputting actions on the joystick, buttons and motions, right? So because it's dealing with the image as input, generally for images you use convolutional networks. So that's what they did. And then they added a couple fully connected layers. And then the output layers are the Q values for all the actions. So you can imagine little green bars here showing how good each of those actions are at every step. Yes? Yes. Yes. I mean, technically, they actually put more than one frame in. I think they put 4 frames because in Pong, if the ball's moving, if you just see a snapshot of the ball, you don't know if it's moving this way or this way or this way. So they put, I think, 4 frames, and that lets the network be able to, or some people do subtract the previous frame, so you get a negative shadow of the ball, but some way to see the motion, right? But aside from that, generally, yeah. Probably a state. It's not really outputting a probability, it's outputting an expected reward, an expected return, the sum of future, discounted sum of future rewards. So it's a little different than probability. Um, so what's outputted is how good it thinks each of the actions is, how much reward it thinks some reward will lead to if it takes each action. Um, no, it's the complete reward. And the way they normalize, so they take the score in the Atari game, which is up here, and they normalize it across the game. Because some games, you end up with a score of 1 when you win. Some games you end up going up to 1,000,000. So they normalize the scores, and that's considered the reward, is the score. It doesn't need to be a softmax because it's actually the reward, the expected reward, which is probably between 0 and 1, I believe. But it's still, I don't think, technically a probability. I mean, in AlphaZero, they do output the actual probabilities of winning. In some versions of it. They had anyway, we'll get into that not today. So is it really that hard to win an Atari game, to write a program to win an Atari game? Imagine Pong, right? Is it hard? Pardon? Is it? I'm not saying it's easy, but do you think if you gave like a CS student, even first year, like gave them a few days to just for Pong, and they could read any pixel value, could they come up with some if statements thing that could win it, could figure it out? Yes, exactly. That's what's amazing, right? I mean, some people don't realize that and think, oh, you solved an Atari game, but it's really that ability for the same algorithms to be plugged into all the games and do well on most of them, right? I mean, it doesn't solve every single one, but so they use the same hyperparameters for every game. I mean, it's that part I think is really cool. That's why I put Steve on there, because he's excited about that fact. Because if you think about it, you're always twiddling the hyperparameters for every single thing we do. If you listen to what DeepMind says, they're always looking for methods where you don't have to twiddle a lot of knobs. And they do analysis on how much twiddling is needed. So I mean, it's possible to come up with methods that kind of work if you twiddle enough, but they really, I think they're serious about this. So DeepMind's, when you ask DeepMind what is intelligence, they often point to this. Yes? I think so, yeah. It's an emulator. It's running on an emulator. No, it's not the same. It's not the same training process. They're retraining on every game, and they're not recycling the network. They're using the same structure of the network and hyperparameters, but training it from scratch separately on each one. They're not trying to do transfer learning. Yeah, no, that's another problem. Transfer learning. They weren't trying to tackle that here. Okay, so DeepMind has presented in some of their presentations. They point to this old paper about what is intelligence, and they're saying here what it's saying is intelligence is how well you do how much value you've achieved across different environments, but weighted according to how complex the environment is. The K is the Kolmogorov complexity of the environment. So it's kind of a conceptual thing, but basically what they're trying to say is if you have one agent that can solve a lot of different tasks in a lot of different worlds, that's more intelligent than an agent that can do one. So that's their justification for why they're saying this is like a simple form of AGI. That's what they're trying to say. I mean, so I don't. If you don't have to like this equation, but yeah, it's written here. Universal Intelligence, a definition of machine intelligence by Legg and Hutter, 2007. And this slide is from a DeepMind presentation, but they're just quoting the exact equation is in that paper. Pardon? Oh, okay, I haven't read it.
So, my understanding is it's really hard to get the number of complexity, but does DeepMind have an estimation of universal intelligence for an average person playing target?
Actually, I have no idea, but they did measure the performance of humans, and that's what that line is. That's they actually had testers trying the games and to calibrate so they could compare. But I've never seen any more in depth in terms of like putting numbers on this. But this is just a concept. To me, it's a conceptual thing. So let's look back at this complexity. So this is showing how much computation went into the biggest AI training runs recently over the past few years. And I was pointing out that the biggest runs lately are reinforcement learning runs. Okay, it used to be that they were this image stuff. But nowadays, the RL ones are really expensive. But if you look at DQN, there's a real anomaly here. There's many orders of magnitude less than this stuff. And they blew our hair back with a very small amount of compute. And I think that's pretty cool. Like, there's something to be said for that, right? So DQN is taking Q-learning, it's adding deep learning, and then they added this experience replay component. So what it looks like, now we have our reinforcement learning clock cycle model, and now the agent has a deep network inside it, and it has the policy. I represented the training system as separate from the agent. Some people wouldn't like that. I know like Ilya Sutskever of OpenAI, he's like, no, you're never done training. You're always training. So I think he would say, Robin, you should really put that in there. But I have my reason for putting it outside. In the implementations that I've dealt with, the training algorithm is actually the outer loop for the clock cycle. Like it's making the loop happen. That's one thing. And also, once your agent's trained, you can actually jettison all that other stuff. And then you end up with, what you're left with is really just the queue function and the policy, which is just simply picking the largest queue, which is almost like one line of code. So once you've trained your agent, what you're left with is something actually quite simple if you don't need to learn anymore, right? So what's happening here is the training algorithm is saying, okay, agent, here's your next state. What's your reward? The agent gets the action. And it's putting it in the memory. It's remembering a certain number of transitions. It's remembering a certain amount of the past. Not remembering everything, because then we're moving into some other kind of supervised learning territory. Yes? Maybe we can take that offline. I'm a little concerned about time. So here, remember the exploration policy is the epsilon greedy. That includes some randomness. And when you're done, you're not using that. You're just picking the argmax. That's the largest action. Okay. So how does the algorithm work? Intuitively. So when we start, we're just trying some random actions, and we eventually get some reward from the environment. Then you remember the transitions. Transitions meaning I'm starting in state S1. I took an action. I ended up in S2. So remembering the words you get and the states. And then you train in little bits as you go. It's not like fitted queue iteration, FQI, is like you train on the whole batch of your history. But that's not how this works. This works in little mini batches. So the way it happens is it picks a few random memories from the experience replay memory, and then it makes that literally into a little mini batch for training the TensorFlow network. So whereas usually you would, when you were training a deep neural network, you'd iterate on batches all the way until you trained. Here you don't do that. You just do a little step, a little train step. Then you play the game up. You take one more action in the game, then you train a little mini step, and then you take an action. So you're alternating between playing and learning. And so that's online learning because you're learning as you go. Yeah. Maybe let's get through these and see if it's clear to you. So you're stretching the rewards back in time, not the rewards, but the expected rewards through the Q function. That's using TD learning. And then you're training using deep learning to learn that stretch, that expected reward from the state. And deep learning is helping you generalize over similar states. And then the final, when you're done, you can play in greedy mode with epsilon 0, basically. So another way to look at it is what are the components here? So TD learning is, I said causality, I don't know if it's really causality, but TD learning is learning how the expected reward works by pulling the expected reward back in time. And then the Q function is estimating the value, as we know. And deep learning is allowing for generalization. So that's to the point, someone's pointing in the back about similar states. Deep learning gives us that. It says this state is so much similar to that one, so I'm going to predict a similar Q value. And then there's the memory experience, the experience replay memory. The purpose of that is if you're just playing the game and you're learning on every step in real time as you go, then all your steps are correlated, like they're very similar. You're on a very similar trajectory. So your deep learning is getting too over myopically focused on this one trajectory because it just keeps learning more and more about this one trajectory and is losing the ability to generalize to other trajectories. So by doing this method of having the experience replay memory and pulling random memories, it's overcoming that focus on the current moment. Does that make sense? So there's two. This happens in two steps. There's the forward step. That's actually playing the game normally, right? So the agent gets the state. The environment gets the agent picks the action, gives us the environment, and then the environment gives the reward. That's just a normal step through the cycle, right? But then there's a backup step, and that's when the learning happens. So it's going forward, back, forward, back, forward, back. It's playing a normal step in the game, and then in the background, it's storing the memory, and it's doing a little training step on the network. And that's what I mean by online. It's playing and learning at the same time, but one after the other. No, Dyna would add planning to this. So this isn't doing any planning. It's just the Q learning part is working kind of just like Q learning that we learned before. But yeah, Dyna would be adding planning. So it's doing mini batch gradient descent. Like it's literally pulling a few random memories, training on those, and it wants different memories every time so it doesn't get myopically focused on the current trajectory. Okay, so formally, you can go through this if you want. This is directly from the paper. But actually, there's two versions, because they published it in 2013, and then they came out in 2015 with the letter to Nature, and that had a slightly different thing. They did a little change in it having to do with this. There's two Qs now. There's Q hat and there's Q. I'm actually not going to get into that today because there's not time. It's kind of just an implementation detail that It makes the training more stable, and you should probably use it, but it's not that interesting. This is just showing the different states. This is from the back of their paper. It's showing the t-SNE embedding of different states, and it's saying that it's showing how. This is showing a visualization of the last hidden layer in the network, and it's just showing that the network seemed to group similar states together. So basically, the whole idea of using deep learning to generalize seems to be working based on this. The network has to figure that out on its own. So DQN is not like the ultimate algorithm. There's a lot of limitations to DQN. It's really not perfect. A few of them are, well, it can only handle discrete actions. TD0 is only learning one step, so it can be kind of slow to converge. The experience replay memory, they use a pretty big one. They use like millions of frames of memory. And now it's not remembering the whole screen. It's just remembering, no, actually that's not true. It would have to remember the state and the next state. I got to think about that. Let me check how much it's putting in the memory. Because in my systems, it's actually remembering the whole board state, which in an Atari screen is actually quite a few pixels, right? So that's I think that's what it's doing. It would have to remember, this is the entire state, and it's remembering millions of those. So it actually takes a fair bit of memory. So and you can reduce that size of the experience replay memory if you wish, but you risk your stability of your learning. Epsilon greedy exploration can be kind of a weak way to explore. There might be better strategies, like AlphaZero doesn't use this. It uses better exploration strategies. And model free is quite stupid. This is to your comment about DynaQ, which would be model based, so it's able to plan, but this doesn't do that. So it can't think ahead. There's other limits too that I just thought of on the way here. Let me think if I can think of them now. Maybe it'll come to me later. Anyway, since then, there's been a lot of work on variations on DQN. So here was a paper that was looking at, I guess this thing comes up when I move my mouse. But there you go. That's from a paper that's looking at the kind of lineage of these things. DQN's in the middle back then. You can see a lot of things have happened since then. Oh, this is just on that fixed target. I'm going to skip that. So double DQN, remember when I said there was a Q and a Q hat? They actually put another network in here, and it's like a replica of this one, and they update it periodically. That's what that Q hat is. So that was one of the variations. They also had a variation where they made a prioritized replay, which means the replay memory, instead of just pulling random memories, it actually considers how informative that memory is to the current state of the network. That means it prefers to pull memories that it has still a lot to learn from. And it does that by looking at the TD error. So that actually makes learning faster. Because you can imagine, if you keep on learning on memories that you already have mastered, it's kind of a waste. So this prefers pulling memories that it hasn't yet mastered. Then there's distributional DQN. This is a very interesting one, where they're modeling, instead of just modeling the reward, they model the reward as a full distribution, like actually 51 buckets. And this helps learning a lot. So here's an example of playing Space Invaders with the distributional reward. And you can see the different colors. It's hard to see here, but there's actually different curves of different colors, and the colors correspond to different actions. And then you can see sometimes the zero, the return 0, that means it thinks there's a good chance it's about to lose the game when that suddenly spikes up. So you can see there's a lot more information coming through to us when we're able to witness the entire distribution. It's funny, I saw Rich Sutton watching this presentation from the author of this paper, and he didn't seem very happy about it. He actually walked out, which I think was... Yeah, good question. So, yeah, I think you'd go with expectation. But to be honest, I haven't gone in depth into these papers. So, and you're welcome to. I have the references. Dueling DQN. This is an interesting one. It's kind of simple, but it works well. So, where you have the state action values at the very end in a normal DQN, in dueling, you split up the state value and the action advantages. I don't know if you remember in the beginning I said value-based methods can use a Q, which is what we're doing, or it can use a V, a value function of a state, or an A, which is an advantage of an action in a state. And so what this is doing is decomposing the Q into the A and the V. A and the V, yes, so the A and the V. And then recombining them. So in the end, you get the same thing. The output is exactly the same. But in the internal structure, separates these two things, and that provides some inductive bias that helps the network learn better. So that simple structural change ends up bringing better performance. And then there's noisy nets. So that takes DQN, and instead of using epsilon greedy, it adds some noise neurons to the network. And then it actually trains the noise neurons in a way that trains I think it's the mean and the variance of the noise for these neurons. I can't actually tell you the in-depth details about that further than that. You can look at the paper, but it helps. Then there's n-step DQN. That's the thing we mentioned before about looking more than one step ahead. Instead of just pulling the reward, and by looking ahead, I don't mean planning ahead. I don't mean that when it's playing, it's thinking about what the possible 2 steps down the road are going to be. That's a different thing. What I'm talking about is how much it pulls the reward backwards each time. How much it pulls the Q learning back. And I remember I said you're walking through a door and you just mark what you see on the next room, or you can look through multiple doors. That's what I'm talking about here. Multiple steps. So you can do n-step DQN. Now, there's a paper called Rainbow DQN. And this is either the state of the art or close to the state of the art of DQN today. This takes the vanilla DQN we learned about in the beginning. It adds the different improvements that we mentioned. And compared to the gray line, which is the vanilla DQN performance was on Atari, all of these things combined result in this much more powerful learning system. So you're strapping on all these, and this can be very inconvenient in the code, but you're strapping on all these things, and together you're starting to get something. It combines them all together in a particular way. Well, each of them are kind of orthogonal, right? Like you can use different type of noise, and then your memory is improved by using the prioritized replay, and then you're doing more than one step ahead. Like all these things are orthogonal. So well, if you look at n-step Q just as one example, or n-step TD, it's actually making the Q values converge faster to the true Qs. So that part doesn't directly have to do with the neural net. Some of these things have to do with the neural net. Some of these maybe don't, right?
So like you also see it as improving the Q function itself.
Yeah, well, that one is improving the Q function itself. Yeah, some of these are definitely about the neural net, like the dueling DQN is all about how the network's structured, right? Yeah, so they're more orthogonal. Yes. Oh yeah, good question. I actually don't have that slide, but I think it's probably in this paper. But it would be better. It would be better. So let's just look at a bit of code. OpenAI Gym is a standard environment. It's like the MNIST. I say MNIST of reinforcement learning, and you can plug in your reinforcement learning agents to it. They also have a series of baselines. That means agents that they coded up, and they coded them fairly well. If you look around on the internet, you will find a ton of implementations of DQN, and some of them are really bad, but this one's not. So you can try that. And this is how it looks remember when I said when you have, so here, the DQN training algorithm is controlling the environment and the agent and all that stuff. So that's what this thing is. So here's deepq.learn. That's the training system. And it takes an environment, right? And it takes an input of a model, like an actual network model. So this is like it has a little helper function that builds a network for you. But that's just saying a network with 64 hidden units. A learning rate, so you put in a few, here's your epsilon. And here that means it's a schedule. The epsilon has a schedule of it's getting smaller over time. And that one line trains your agent on that environment. And when you're done, you save it, and now you have an agent that can solve this one task. So, I mean, at this level, it's kind of simple. So I've been using Keras RL. I don't know. I just like it because it's Keras, and Keras is just nice to read. It doesn't have all the latest algorithms in it, but it has DQN, and it has a few good ones. So I've been using it because I like Keras. It has a new maintainer, so I think it may get legs. But there's other ones aside from OpenAI Baseline. There's TensorForce, which is a TensorFlow-based library for this type of stuff, and there's a whole bunch of other ones. Your mileage may vary. So in Keras RL, how does it look? A similar thing. You create your environment, define your action space. Here you're building your model, your simple neural network, and then you set up your experience replay memory. You set up a policy. In this case, it's using Boltzmann policy, which is more like sampling from a softmax. So here, this is what I meant. You don't have to use epsilon greedy. So this is using more of a softmax type thing. And then the DQN agent actually means the training system, the training algorithm. And then you compile your network. Fit is actually training the agent on the environment. So that's the line that actually does all the work. And then you save it. So who actually made the DQN paper? So Vladimir Nie. He PhD at U of T under Jeffrey Hinton. Masters of University of Alberta. You'll notice some of these people have ties to University of Alberta. Why is that? Because Rich Sutton is like the godfather of reinforcement learning. He's from there, as you well know. I think you studied under him, is that right? Cool. So David Silver, PhD at University of Alberta. And then Corey, he did his PhD with Jan LeCun. And there's some other people, but generally these are the guys you hear from more. So it's just interesting these guys have ties to Canada. Like, I mean, in my perspective, DeepMind, this team is the very cutting edge of reinforcement learning today. They're coming out with papers that are just ridiculous all the time. DQN was just one in a long series. So for me, it's interesting to know what they're about, right? Okay, this is just a reminder. This is a straight quote from Vladimir, is that none of these things are figured out. Like, if you look at a lot of things they did in DQN, they're just like, well, that works, you know. Is it the best thing? I don't know, but it works, right? It's amazing they found a way to make it work, but they're not claiming that it's somehow perfect or that you couldn't find a better way. So I think that's kind of exciting, and it's kind of humble for them to say that. So any questions on DQN? And then, yes? Or a what? Yeah, so if you have an environment where things get hidden sometimes, then you can use a recurrent network, an LSTM, to provide some sense of memory, so that to overcome that hiding of things. Does that make sense? So they actually will use that to overcome that. But I think the structure of the network should be designed to get you the inductive bias that you need for your problem. So that could be different for every problem. This is a CNN because it's an image-based environment. But other environments, if you have a medical environment, it would probably not be image-based, and you would be looking in a different. And the other thing to note, and the OpenAI guys say this very often, is that in reinforcement learning, the deep learning, the use of the deep learning networks is a little different. Like John Schulman would say, batch normalization and dropout doesn't help him in his deep RL for some reason, and they don't even really know why. Fancy architectures in your network doesn't often help much, which is like often the first thing that people try to do. So RL is a little bit different in how deep learning works out. Your loss function. So your loss, let's see. What you're trying to do is you're trying to match the Q values, right? You're trying to train to predict those Qs. Pardon?
So in the training, the model don't know the ICQ.
Yes.
So how to compare the Q?
Yeah, because you don't have one, right? So it actually uses the prediction from its own network. Remember we had this slide here which showed the here. So you would actually use the Q predicted from your own network to train your own network. It's a weird kind of chicken and egg thing. It's very strange that it works sometimes. I mean, sometimes it seems very strange that it works. But you're actually using a prediction, adding the reward, and using that, comparing that to your prediction. Yeah, you do a regular training step, a mini batch. If you're really curious about the details, I encourage you to look through the code of some of these. Okay, so there's a few things I didn't mention. Since I did this, I guess I've been really focused on these very glitzy, glamorous, large training runs, right? But that's not really what all that RL is. And so I amended some of these slides to say medical treatment is an important case for reinforcement learning, and the concerns there are quite different than what we dealt with at Atari and Go. In medical treatment, you're not going to be doing epsilon greedy exploration. It's just no way to do that. And so here, before I just said simulatable, but actually you can also do it if you have existing data. You don't have to simulate. Sometimes it's impossible to simulate what's happening with patients. But you can actually use past data. And like I said, some of the papers that I was looking at were using these methods, but training on past logs of how patients, actions that were taken on patients and the results. And so in that case, you would probably use batch learning as opposed to this online method of doing the mini batches every step. But there's totally different angles on RL, aside from the glamorous stuff that you hear about. Actually, if you really think about these are not very useful, most of these, right? Okay, AlphaGo, 0, AlphaZero. This maybe can be used to design networks, maybe, but Dota, Atari, what's the point of all this stuff? It's impressing us. I think it's kind of it's like a bat signal saying, we're really smart, come work with us, But what is it really accomplishing? I don't know. We'll talk about the game ones in a future talk. But the medical RL, there's a real opportunity there to actually make medicine smarter, maybe, right? But other things come up when you try to use this. I don't know much about medicine at all. Actually, I would say nothing. So I apologize in advance for even talking about it. But the types of things, because I'm ignorant, but the types of things you will care about are like you want to know what kind of confidence you have in the predictions of your system, right? I was just trying to look for that slide of limits. So that should be in here. DQN gives you no sense of how sure you are about that. I mean, I guess the distribution will maybe give you a little bit of a sense, but it's still. I think a clinician would want a lot more than that. And it doesn't give you any explainability. Why is it telling me to take this action? Why is it telling me to give that patient that drug and that dosage? Well, DQN's not going to help you with that. Now, you could use Q-learning with a decision tree, and suddenly you have a very explainable model, right? But it's not going to fit as well. It's not going to fit as smoothly as your neural network. But at least you have something you can explain. Where there's other methods, if you look at reinforcement learning in medicine, they will be talking about Bayesian methods and combining that with some of this stuff. So in terms of next steps, so this is the second talk. The first talk I gave was more of an intro to RL. That was in the beginning of the slide deck. I have some other talks that some are partially ready, some are just kind of concepts, but I wonder, what do you guys want to hear about? Do you want to vote? I may totally ignore your vote, but let's say, who would vote for the self-play multi-agent AlphaZero and AlphaZos? Who would vote for that? Okay. Well, which part? Okay. Well, self-play is like basically when you have these agents that are playing against themselves, like AlphaZero was trained by playing itself, and it got really good by doing that. So I made a system that I call AlphaZos, which I showed you some screenshots of, that's using self-play to learn simpler games that we can discuss and reason about. Actually, it can be extended to all sorts of games. It won't be as efficient as AlphaZero, for sure, but it's using deep reinforcement learning to play games with self-play. So I wanted to learn about multi-agent situations, and so that talk would be about those, and also AlphaZero, like how does that work? Okay, with the next one, reinforcement learning in medicine. Okay, cool. So caveat, I should have told you this before you voted. I don't know much about medicine, because I'm actually reading in the medical literature. When they mention reinforcement learning, what do they mention? What are they talking about? What methods are they using? What are they trying to solve? What ends up, what are the results? So I was just going to go through few papers that I found that it's like chemotherapy, HIV, some anticoagulant dosage or something like that. That RL is going to be always a sequence of actions, right? If you want to just predict one thing, like how much dosage does this person need this one time, you don't need all this mechanics. You just use supervised learning, much simpler. If you can never use supervised, prefer that. But supervised won't help you play Atari, Go, or solve these like the dosage problems where you're having to take doses over time, right? Okay, what about actor-critic methods? Any votes for that? Okay. It's another type of RL algorithm aside from Q-learning that combines the value functions and the policy functions together. And so a lot of things that are DeepMind and Google will prefer actor-critic most of the time. And it's nice because it's actually theorized to be how our own brain learns, and it can output continuous actions or discrete. So it's very flexible, and there's many interesting variants of it. What about selected? Why did I write that? So some very, very up-to-date papers, maybe from DeepMind, like some more exotic stuff. Any interest in that? Not as much. Okay, cool. What about AGI? Okay. All right. Pardon? Yeah, not for me because I haven't started writing that one yet. So I've started writing the first two, so you'll probably just get whatever one's ready first. But that's good. That's good to hear. So any other questions, or otherwise we can chat afterwards after I get this mic off. And thank you to Bruce for the incredible AV and for the video last time. If you haven't seen it, Bruce posted the video on YouTube, and it's a really crystal clear video of my first talk. And if you didn't see it, you might get some more out of that one. Okay, thanks very much for coming, guys. I really appreciate it.